All right, well, hello AP Physics students, and welcome to this video, which is meant to debrief the great soup can race of 2019, which, again, I apologize, I rigged, but it was for a purpose. So I just want to talk through the soup can race itself, and then on the next slide, I'm going to kind of more fully discuss this idea of rotational kinetic energy in conjunction with rotational inertia. So, the great rigged soup can race of 2019. What I have here, we're just going to kind of isolate two things. I have a can that's filled with just water. Okay, so this is like the can of chicken broth that I had on Friday. Now, this one here, this is just a solid cylinder. Okay, so this would be like our cream of chicken soup or our cream of mushroom soup that we were looking at. Now, we all got to the point where we said, okay, these things both have gravitational potential energy at the top. And we also got to this idea that they have Ke at the bottom, of course, because they're moving, right? So all that PEG is turned into Ke. But the difference here now is that these objects are rotating. So yes, they're moving linearly, but they're also rotating. So that means that that PEG that we had at the top actually gets turned into translational kinetic energy plus rotational kinetic energy. All right? So conceptually, that's what's going on there. This PEG is getting turned into two different types of kinetic energy, essentially. Now, who wins the race, though? Well, the one that has the greater amount of translational kinetic energy or linear kinetic energy is the winner. But how do we actually determine that? Well, this is an extreme example of what we should have seen in that pivot interactive, where you saw that the radius and the mass of those rings didn't really matter. But what did? The distribution of the mass itself. Okay? So, again, this is an extreme example, but with the solid cylinder, all of this mass immediately begins to rotate. However, for that can of chicken broth or this can filled with water here, only the mass of the can is actually rotating as it's moving down that ramp. So what does that mean? Well, for the can of chicken broth or this can of water here, that means that all the mass of that water is being turned into translational kinetic energy, whereas only the mass of the can itself is turning into rotational kinetic energy. But that's getting split a little bit differently with that solid cylinder. More of the mass of this is getting turned into rotational kinetic energy. Therefore, it ends up having less translational kinetic energy at the bottom. So as we saw, the can of chicken broth won by a landslide. And to go a little deeper in that, like again, if this can were invisible, what would we see? Well, this water wants to remain in the position that it's already in because of its inertia. So it just wants to linearly move down this ramp without changing its shape or form. Okay, it wants to stay in the position that it was in. However, because this solid cylinder, or in our case, the cream of chicken, it's more viscous, so its mass is going to rotate with the can itself. Okay, again, creating more rotational kinetic energy, therefore less translational kinetic energy. So conceptually, that's what's going on. But on the next slide, I'm going to go into a little bit deeper about what rotational kinetic energy is in terms of rotational inertia and rotational inertia's impact on rotational kinetic energy. All right, so here I have several different objects. Now, if we look at the first object that I have here, which is a block, well, let's take a step back. Again, all of these objects have gravitational potential energy at the top of the ramp. We'll assume that they're all the same mass, just for simplification purposes. But we know that this thing is not going to rotate. All right, so all of its gravitational potential is getting turned into translational kinetic energy. That means that this block is going to win by a landslide. But let's just take a look at these two objects here. So we have a solid cylinder and we have a hoop. Well, who's going to win between those two? Who's going to get second place? Because we know that this black is going to be the landslide winner. Well, what this comes down to is which one has less rotational kinetic energy at the bottom. Okay, so whichever one has less rotational kinetic energy and therefore more translational kinetic energy, that's going to be the winner. So what we can do is we can model these two mathematically. So I'm going to set up, we'll start out with the hoop here. I'm going to set up a conservation of energy equation. So I'm going to say mgh at the top is going to equal 1/2 mv squared. Okay, that's our equation for translational kinetic energy, plus 1/2 I omega squared. Now, here what we can do is we can plug in some different things in our rotational kinetic energy equation. Okay, notice how similar this equation is to our translational kinetic energy equation. Remember, we're just plugging in those rotational terms now. But what we can do is, I know that the moment of inertia of a hoop is mr squared. Okay, what this is telling us is that all of the mass is located at some radius from this axis of rotation, which is right at the center of this hoop. Okay, but I also know that my translational velocity is radius times omega. So what I'm going to do is I'm going to erase this stuff here. I'm going to plug in these new variables here. So what I'm going to do is I'm going to plug in my equation for moment of inertia, and I'm going to plug in omega in terms of translational velocity. Okay, so now what I'm going to do is I'm just going to simplify this thing way down. So if I square this term right here, well, that's going to leave me with, okay, I'm going to get rid of that. I'm going to end up having velocity squared. That's going to get rid of this r squared. My masses end up canceling out everywhere. So now from here, I can just do some simple algebra to simplify this down. So what I'm going to end up with here is GH is equal to, let's see here, v squared. So that then gives me a translational velocity for the hoop of square root of the acceleration due to gravity times the height. All right, so that's how fast that hoop is moving at the bottom of the ramp here. Now, I'm going to do the same thing for our cylinder. All right, so my moment of inertia of the cylinder, and again, you can look this up yourself, but it is 1/2 mr squared. So notice that we have a little bit of a different distribution of our mass. We have more mass located around the center of our axis of rotation here. So what does that mean? Well, let's check it out. Let's check it out. What does that mean in terms of the translational velocity? So I'm going to write out that conservation of energy equation again. So 1/2 times 1/2 mr squared. Oh, there we go. All right, now I'm going to simplify this algebraically again. So my r squareds are going to cancel out. Again, my masses are going to cancel out on both sides. So that's going to leave me with GH is equal to 3/4 v squared. So I end up then with the translational velocity of that cylinder to be the square root of 4/3 times GH. So what are we seeing here? Well, we're seeing that that cylinder is going to be reaching the bottom first because it has a greater translational velocity at the bottom of the ramp here. Now, why is that? Well, again, the cylinder here has more mass located around the center or the axis of rotation compared to the hoop. The hoop's mass is all along that radius. Okay, so what does this mean for rotational kinetic energy and in terms of rotational inertia? Well, the higher the rotational inertia of that object, the more rotational kinetic energy you're going to have. Therefore, the less translational kinetic energy you're going to have at the bottom of this ramp. Now, we could model this for a solid sphere and a hollow sphere as well. And what we're going to end up seeing is that this solid sphere has more mass located around its axis of rotation. So it's going to beat this hollow sphere down the ramp. Once again, because it has a lower rotational inertia. So really what this comes down to when you're looking at rotational inertia, it comes down to this fraction right here. Okay, it comes down to this ratio. And we're going to understand rotational inertia a little bit more and how we actually get these equations in the next video lecture, which we're actually going to use some integration to solve for some of these. But all this is it's just giving us a distribution of where that mass actually is in terms of an axis of rotation. All right, so again, the soup can race was a silly means to an end, I guess you could say, giving us a very extreme example of how mass can be distributed to then affect its translational and rotational kinetic energy to then win that race. But the main key here is understanding that the higher a moment of inertia is, the more rotational kinetic energy you're going to have. And that, therefore, it's going to have less translational kinetic energy. And it's all dependent on the rotational inertia. And again, we're going to understand more how rotational inertia is actually derived for various objects that may be uniformly distributed, but we're also going to look at ones that have, kind of a goofy distribution of mass, and we're going to be able to solve for the rotational inertia of kind of those funky objects. So I hope this video helped in debriefing and kind of giving you an overview of what rotational kinetic energy and rotational inertia is all about. And then I hope the next video lecture also helps us more fully understand rotational inertia. Take care, AP Physics students.